Hi there, good morning everyone. Wakey wakey, as somebody wrote in the chat. I hope you're sufficiently awake for today's lecture, which is going to be about asymmetric cryptography. So a brief orientation and recap of where we currently are. You already heard 2.5 lectures about cryptography where we covered symmetric cryptography. So functions where Alice and Bob completely trust each other and share the same key material. And we had a look at several functions in this context. Some for protecting integrity, like hash functions and max. Some for protecting confidentiality, like encryption schemes. And we also had a look inside of those encryption schemes by looking at the primitives. And we also saw that authenticated encryption actually solves both of these problems for us. So it's essentially the one building block that you need for secure communication. However, we're going to see that to start communication, you first need to establish it, in the sense of agreeing on a common key material. And this is going to be the main topic for today. As a reminder, we will have one more crypto lecture left, which is going to be next week, where we're going to have a look a bit further up in the hierarchy and the stack of cryptography closer to practical applications. But the block here is a bit variable, so I'm still waiting for your input today. If you have any special wishes, what you want to cover there, I'm open and I have a bit of flexibility in the time schedule to accommodate that. So to repeat a bit what we heard last week, so that you don't entirely forget about symmetric cryptography while we talk about the asymmetric case, here's a recap of the schemes or the types of schemes we heard last week for encryption. So we discussed that there are pure encryption schemes which only protect confidentiality, where both partners, Alice and Bob, can encrypt and decrypt the data and verify the authenticity in case we're not using pure encryption, but authenticated encryption. We also mentioned that there is a third case, which is going to be one of the topics today, namely asymmetric encryption, which is also sometimes called key encapsulation in some cases. The difference here is that in the asymmetric case, not the owner of the key, but everyone can encrypt stuff. And only the owner of the key can decrypt. And we heard a bit about the building blocks for these two types of encryption schemes last week. We saw that inside they have a primitive, which works by iterating a simple round function often enough to achieve security in some sense, where the rounds are controlled by XORing a key produced by a key schedule. And this blue building block can then repeat it in order to be able to handle data of arbitrary size. So this is just for fixed block input sizes and shouldn't be ever used by itself for encryption. Even if it's the AES and everybody agrees that the AES is secure, it's not suitable as a standalone encryption scheme. You need a rule like this, which includes some additional inputs like the nonce to randomize the ciphertext. It may also take other inputs like associated data, and it translates the message into a tag and ciphertext by combining, for example, a MEC and an encryption function. So this is a very brief overview of last week, but you already guessed it. Of course, we're going to do a quiz to recall some of the details. So as usual, head on to Menti. I saw some of you already joined before the lecture started. We're going to have 6 questions today because last week's quiz took a bit too long, I think. So let's wait here on the slide for a little more time while you're joining. You can either copy the code above or head to the description on YouTube where you can find a link to click. In the meantime, I hope some of you have already started working on the exercises and have found some context or some concepts that they know from the lecture, but maybe also discovered some new stuff. For those of you who were confused by the things like the modular inverse and other things in the signature example, maybe a bit of this can be clarified in today's lecture as well as in today's exercise session in the afternoon. Okay, so it looks like a number of people have joined already. So let's just start with the quiz. Let me see. There. So question number 1. As usual, you get more points if you have the correct answer fast. This time it's single correct answers. Which security property of the message does authenticated encryption protect? Is it privacy, collision resistance, confidentiality, or anonymity? Time's almost up. And indeed, like most of you guessed correctly, it was confidentiality. Privacy is a related word that also relates to hiding information. But if you recall, we said that generally privacy is about an individual's right to decide which information about themselves is published and which is kept secret. There are a few people who also use the word privacy to mean something similar to confidentiality, but this is not widely used because it's extremely confusing, because it usually means something different. And anonymity was yet something else. It means the ability of a person's identity to not be revealed from some larger set. So that you can only say somebody from this set did something and not which individual person. Okay, but that was a good start. Let's have a look at the next question. Namely, which one is the lowest layer in the crypto stack? The protocol layer, the primitive layer, the scheme layer, or is it a mode? Lowest meaning the other stuff builds up on top of it. Time's almost up. And indeed, that's correct. The primitive is the lowest layer. Schemes are constructed on top of primitives. So primitive is something like AES. A scheme is something like authenticated encryption with AES. And the mode describes the rule how the scheme is produced from the primitive. So if you think of cooking, the primitives are the ingredients, the mode is the recipe, and the scheme is the finished dish. And protocols are yet further up in the hierarchy and use several schemes to process the data before sending it back and forth. Next question. Which of these is not a design principle for block ciphers? We have here repeating a round function r times, key alternating constructions, Merkle-Darmstadt constructions, and substitution permutation networks, which is not a design principle for block ciphers. Oh, that was a tough one, it appears. So let's just briefly go through the individual concepts. So the correct answer here, because it's not a design principle for building block ciphers, is the Merkle-Darmstadt construction. Because what this construction does is it builds a hash function from a compression function. So there are generally no block ciphers directly involved. They may be somewhere hidden inside, but it doesn't help us to build block ciphers. Let's look at the other words. The first one was repeating a round function r times. Well, this is one of the basic concepts of how block ciphers are built. It's also called the iterating construction. The idea is to have a simple circuit and repeat it many times. We actually already saw a picture of that. The key alternating construction is a special case of this iterative construction. What this does is it builds each round by having an unkeyed round function and first XORing the round key and repeating this combined construction. And finally, the substitution permutation network is a construction approach how to build the things inside the round function for key alternating constructions. So if you look inside a block cipher, you will first see repeated rounds. You will see that these rounds always start with a key addition and that the round function itself is composed of S boxes and permutation layers. So these together are a recipe for building a block cipher. one of the possible recipes, not the only one, but the most important one. Okay, let's head on. Let's hope the rest works a bit better. So, what was the goal of the AES competition? Was it to cryptanalyze an NSA cipher, to replace MD5, to replace NIST, or to replace DES? Okay, close call, but the right one won. So let's briefly go through the answers. It was not the goal to cryptanalyze an NSA cipher, although the DES was a cipher design that was influenced by the NBS, which is the predecessor of the NSA. So the goal was to replace this encryption standard because it had turned out to no longer offer adequate security. MD5 is also a function that was replaced, however not in the AES competition. This is a very old hash function that needed replacement, but that was superseded by NIST's own designs, such as SHA-1, SHA-2, and so on. And NIST finally is the actual organization or the official government body in the US who organizes these competitions. So replacing NIST is definitely not the goal. But replacing this old block cipher was the goal, where DES is Data Encryption Standard and AES is short for Advanced Encryption Standard. So clearly the next step. Okay, we have 2 questions left. Which of these is an authenticated encryption mode of operation? CCM, CBC, counter, and ECB. I guess this is a bit of a tough one because it just all looks so similar. Oh yeah, yes, as expected. However, the right one won again. So let's go through the wrong ones. We all saw them last week. So ECB was the trivial mode where you just applied AES to each block and that's it. No additional operations. And we saw that this has huge problems. ECB is short for Electronic Code Book. Then we last week saw 2 good encryption modes, namely CBC for cipher block chaining and CTR for counter. And we saw that these 2 are good encryption schemes. However, they do not offer authenticity because they do not include a MAC. And CCM finally is the combination of the counter mode of encryption combined with a CBC-based MAC construction. And the result is called CCM, where the first C is for counter and the second C is for CBC MAC. And that's the only authenticated encryption scheme in this list. Okay, final question. This is also a bit more complicated because now you actually have to type something. And the question is, name an operation of the AES round function. So you get a little more time on this one. Accepted names are the long written forms of the name, so not the 2-letter abbreviations. Oh, we have quite a number of suggestions here. So the correct answer is either of this list: subbytes, shift rows, mix columns, and add round key. Let's see, so shift rounds was picked several times, subbytes was picked several times, that's all correct. Someone listed XOR. This is not strictly speaking the name of an AES round function, however, the add round key does nothing except XOR the key to the state. Permutation is also a description of one of the steps thus, but not the name. So if you're guessing which of these was the permutation step, the correct answer is that shift rows simply permuted the bytes, so changed the order of the bytes. Shifting is another name for shift rows, I guess, that you can use here. Shift row, well, that was just a spelling problem. So the correct name is shift rows. Then we have here substitution, which is also a correct description of what the sub-byte step does, but just not its name. But it's very good, I think, that many of you remembered the individual functionality of the steps, if not the actual names. And then, of course, we have things like, well, not knowing, no idea. Encryption is the purpose of the full thing. It's a pity that I can't see all of the answers here, I think. I can see them on my phone. Okay, so 3 of you picked substitution, 6 of you picked permutation, which is great. Then shift, permutation, encryption, blah, 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 I don't know. That's also what 5 of you picked. 1 had sub-bytes correct. Row shifting was a good, so it's a good description of what shift rows does. Then we also have subtract. This is not really a step of the round function. XOR in different spellings, that's all good. That's what 5 of you picked. 2 had shift rows correct. Some had no clue. Another shift rows, blah blah, round XOR shift row. Oh, many of you had shift row with a space. I'm sorry that I couldn't count that. I could only enter 4 answers to be counted correctly. Compression, oh no, this is not a step of the AES round function. So this is a different type of primitive. Blah, 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 blah. Some encoding. No, AES actually does not really do some encoding. So that's rather something that the mode on top would do. Padding is also not something the AES does, but that the mode on top does. Okay, so these are all the answers I can see here. That leads us to the leaderboard. I guess it's a bit more or less close now because the last question was a bit difficult. And the winner for today is Thomas, and if my memory doesn't betray me, Thomas also won last week, I think. In any case, if it's the same Thomas and if my memory serves me right, then congratulations. Okay, that brings us to the actual lecture and the plan for today. Let's have a look, and thanks again everybody for participating, of course. So, what is the plan for today? We first are going to have quite a bit of time to cover only the background we need for introducing the rest of the lecture. So in particular, almost all the time before the break will actually be spent on this top part here, where I want to recall what the idea or the goal is that we're trying to solve, and also have a bit of a recap for what you already learned in discrete mathematics, namely the topics of modular arithmetic and of hard problems in mathematics, in complexity theory. And shortly before the break, hopefully, we're going to start and work on actual schemes. So we have a key exchange scheme to start with, namely the Diffie-Hellman key exchange scheme that some of you already named in the first lecture under ciphers you already know. So I guess you've already heard a bit about this, maybe also in discrete math. Then we're going to look at asymmetric encryption by means of RSA, and also a bit more at the general concept of trapdoor one-way function, which is the more general description of what AES is doing, RSA is doing, sorry. Finally, we have a look at signature schemes, which can be built in a very similar way as encryption schemes, in some cases, for the case of AES, RSA. Something's wrong with my memory today. Okay, so let's first start with the motivation for today's lecture. So we already heard quite a bit about symmetric cryptography, and we saw that it's efficient, it gives us confidentiality and integrity, so it looks like we're pretty much solved. However, there's one thing we didn't solve yet, because we always assumed that all participants, or both Alice and Bob, already had a pre-shared key to begin with. And this is the assumption that actually poses a huge problem in practice, as you may already have guessed. And one of the reasons why it is a problem is when you look not just at Alice and Bob, but at a larger population set. For example, every internet user. Or it's sufficient to look at just one company or the university or so and look at the list of people in there who would like to communicate with each other. Because if the system has n users, like n equals 2 or 5 in this example here, then how many key pairs do we need? Well, every user needs a key with every other person they want to communicate with. So every of the n users needs a key for n minus 1 other people. Now in this, of course, we're counting every key twice, because from Alice to Bob and Bob to Alice, so we divide by 2. But this is still a huge number. It's quadratic in the number of users of the system. What does this mean? Well, among other things, adding new users is going to be very expensive and complicated, because whenever a new employee or so starts, you would have to start exchanging key material with every existing user of the system. It's also completely impossible to apply this directly in the context, for example, of the internet, where you're often first time visiting some site, some vendor, some other communication partner that you have never met before, but that you would like to start talking to. And this is why, there's one other problem, and that is that in symmetric cryptography, we always assumed symmetric trust relationships, meaning users trust each other equally. Alice wants to talk to Bob, Bob wants to talk to Alice, and they trust each other. This is not necessarily the case in the real world. So in particular, in some cases, you want to have properties like later being able to prove that somebody signed something. For example, if you're talking to someone and you want to sign a contract or so, it's not possible to do that with a symmetric key. Because if we did that, first, nobody else could verify it, because only we had the secret key. And second, both parties would have had the key, so nobody would later be able to prove whether Alice or Bob was the one who generated, for example, the MAC tag, because both had the same key. So it's not possible to really associate something with one of the people involved. It's centered on the team of insiders. It's not centered on the individual users and their perspective. And non-repudiation is an example for this sort of property. If you remember, this means in German Nicht-Leugnbarkeit, so not being able to deny at a later point that you send something or sign something. And this is where asymmetric cryptography enters the playing field. So here's a sort of schematic view of what authentication and encryption, so authenticity and confidentiality, mean in the symmetric and the asymmetric case. We always see our Alice and Bob or multiple Bobs here. And I'm representing here the encryption by an envelope, as in hiding the information, and the authenticity as a signature or as signing something. And what I've also here is a frame of all the people who have access to the secret key material and who are insiders, so to say. So in the symmetric case, it's always all communication partners, Alice and Bob. Both have the key, they're both the insiders, and we need to trust everything inside this golden box here. So they both can send each other hidden stuff and authenticate to each other. Whereas in the asymmetric case, there's only one person who has the key, Alice. And in the encryption case, Alice has the key, and this means that everybody else can send messages to Alice without having any secret knowledge. And in the authenticity case, it's the other way around. Alice, the owner of the key, is the person who can sign stuff, and everybody else can verify it. So that's the general outline. Let's see at what schemes we have in asymmetric cryptography. The first, and arguably the most essential, or the one that we motivated so far, is key exchange schemes. So in this, we have actually two key pairs involved. We have Alice and Bob, and they try to agree on a new key that they can later use for symmetric encryption, like for AES. And what a key exchange does is it sends some messages back and forth, so that usually both users can influence the key, the resulting symmetric key, and both of them learn or derive the key. So they send each other messages so that afterwards both of them have the same shared secret key in their possession. So both are able to derive it. And usually, not always, but usually both of them also influence this key. There's also the encryption case, which we already pictured on the previous slide, where Alice can receive messages from everybody, meaning everybody can encrypt and only Alice can decrypt. And usually this is actually not used for communication like the encryption schemes we saw so far, but it's only used typically as a replacement for key exchange schemes. Because instead of exchanging keys where both influence the key, we can also simply use one of these schemes to encrypt a key that Bob, for example, chose. So Bob chooses an AES key, encrypts it with an asymmetric scheme, and sends it to Alice. And only Alice will then be able to decrypt this key, and then they both have the same key, but only Bob influenced it because Bob chose it and sent it. So this is the most frequent application actually of asymmetric encryption, just encoding the key. So it's usually not used to encrypt large amounts of data. And finally, we also need to talk about authenticity, of course. In the case of asymmetric cryptography, we call authenticity, or schemes that provide authenticity, signatures. So Alice, the owner of the key, is the person who can authenticate messages, put the signature to them, and everybody else can verify it. So let's now look at some application examples of all of these schemes. First, for signatures. So here are some of the most widely used applications of signatures. First, maybe one of the more obvious ones, because you may already have received something like that, signed emails. So if you use, for example, GPG to sign, GNU PG to sign your emails, you often get some encoded stuff at the end, which is called a signature. You can also, or you may also have yourself used electronic signatures like Handysignatur or the previous Bürgerkarte, where you can sign electronic documents such as PDFs. And you may also have received stuff like that. So for example, I think one of the Studienbestätigungen type things that you get is signed electronically by TU Graz. You may have used it, for example, for some Amtsweg or to join in a petition or something like that. You also have unwittingly probably used signatures as part of one of these applications. So whenever you have received software updates, these are usually signed by the vendors of the software. For example, if you get a Microsoft update, there is a signature from Microsoft that validates, so to say, the code you receive. And you also use it every time you open up an HTTPS connection, because these connections usually involve certificates that certify who the other party sending you something is. And the way that this is certified is by means of signatures. We're going to have a bit of a closer look at this in next week's lecture. And finally, there are quite a number of other applications that use signatures in some way, also usually for you to confirm, for example, a transaction in Bitcoin or something like that, or in other digital currencies. And there are way more of them, but I think these are some of the most widely used ones. Now for the other scheme, where are we using key exchange schemes and asymmetric encryption? Usually, or most frequently, this is as part of communication protocols, such as, for example, TLS for browser security, so HTTPS connections, when you build those up, or also the IPsec protocol, which is used whenever you use a VPN connection, or as part of SSH connections, for example, when you connect to a server or something via the shell. And for asymmetric encryptions, the applications are actually very similar. I think key exchange schemes are used more often instead of plain key encapsulation schemes, but for example, SSH supports both of them. Another place where you actually hear the word asymmetric encryption is, again, when you're signing or when you're encrypting your emails. with PGP or SMIME or similar, then you also usually first wrap your secret key that you're going to use to encrypt the email in such an asymmetric encryption scheme, and then you send the AES encrypted main content of the email plus the encrypted AES key, which is encrypted with an asymmetric encryption scheme, to your recipient. So the encrypted key is embedded together with the encrypted message. I do assume that you already know some of the concepts that we hear today, because some of it was already covered in discrete mathematics. ECDH intensifies, well, not immediately. Actually, to disappoint you, we're not going to cover ECDH too much in the lecture, but just part of it, and you will hear the rest in the afternoon. So, but before we jump into that, I would be interested in how much you actually think you remember from this stuff, because I believe that many of you have already heard some of it, but I'm not sure how many, and I'm not sure how much you remember. So I would be interested in how much you think you know about RSA encryption, about signatures, about Diffie-Hellman key exchange, and about the mathematical background, such as modular arithmetic. Just that I get an impression. I guess some of you haven't heard any of it because they didn't take the corresponding courses. I also don't know in which years which of these schemes are covered in discrete math. I'm just not sure. So what does it look like? It looks like you have heard least about signatures so far. For Diffie-Hellman, it's probably the most torn. So some people have heard absolutely nothing and some quite a lot. Probably those with quite a lot may also be the ones who already took a go at the exercises. What surprises me is that most of you feel most confident in the mathematical background. That's really good news, because it will make understanding the rest a lot easier. But here we also have the full range from no clue to I'm super confident. Okay, but that gives me a good impression. I guess that means that I can go over the math background potentially a tiny bit faster, and I will take a bit longer maybe for the signatures. If at any point you find that something is too slow or too fast, let me know and I'll try to adapt. Okay, then let's head to the actual content. I'm sorry, there's no cat inside. She didn't want to join. See, she left right before the lecture started. Okay, so a short recap about, or not so short recap about modular arithmetic, and maybe also some notation that you may not have seen before. So in particular, most of the time in the rest of this lecture, when we're talking about numbers, we're not going to talk about float numbers at all, I think. We're going to talk about integers a bit, but most of the time we're going to talk about a certain set of integers, namely the set Zn, as written here on the top. So the big Z like the integers, but with a small subscript n. And this n in the subscript refers to the modulus that we are using. Modulus means that we take the integers, all the integers, but we divide them into classes. And we put two integers in the same class if they have the same remainder after dividing them by the modulus n. We also say that we compute modulo n, or that we reduce the numbers by n. And since there are there are n possible remainders after division by n, namely the remainders 0 to n minus 1. So if some of you are not so familiar with English math terms, I'm trying to translate the most important ones. So in particular, the remainder after division is the Rest nach der Division. Most of the other words are pretty much the same in German. Okay, so we put when we put two integers in the same class, so if they have, for example, both remainder 1 after dividing by n, then we also say that they are congruent modulo n. And we usually write this by writing this equation symbol with 3 minuses, and by adding this mod n in braces after the end of the equation. So this is the super tidy way of writing this. Sometimes we're lazy and we're just agreeing that the data type of both a and b is to be in Zn, and then we just write a equals b, and we actually mean just that the remainder after division is the same. So if you catch me being lazy, maybe notify me. I am sometimes, but the proper way to write it down would be like this. So if you compare this with the modular operator that you know from programming, then we can say that two numbers are equivalent modular n. So this statement is the same as saying that you apply the modular operator on both sides of the equation. So you compute a modular n with the percentage sign in most languages, and b modular n on the other side, and both results are the same. But in maths, we usually only write mod n once in braces at the end, which means it applies to both sides, or the equality is only when we apply this modulus. So to give you a picture to remember, here is an example of computing modulo 11. So the classes modulo 11 in Z11 are labeled with 0 to 10. We don't use any special notation to indicate that these are classes and not integers, because it's going to be more or less obvious most of the time. And so, for example, the class 0 contains every number that is divisible by 11, any integer. So it can be minus 11, 0, 11, 22, 33, and so on. The next ones are all that have remainder 1 after division. That's maybe important to note here. So if you look at the negative and the positive numbers, they aren't the same. So it's not the same absolute value on both sides. Because, for example, 12 equals 1 modulo 11, but minus 10 also equals 1 modulo 11. Because if you add 11 once, you get 1. So in particular, minus 12, for example, would not be a correct member of this class, because minus 12 equals minus 1 equals 10 and belongs in the very last class here. I hope that's reasonably clear. And because this sort of runs in a circle, I also often illustrate it as a circle where the numbers are like in a clock from 0 to n minus 1, where n is our modulus. Okay, so the interesting thing, or the nice thing about working with modular arithmetic is that if we do all our operations and then reduce the result modulo n, then we get a so-called group, which is simply as a way of saying a set of numbers which has some nice properties, such as the operations are associative and commutative. We don't explicitly care about that, we just implicitly do it anyways. The interesting thing is that we have two types of special elements. The first one is one where we have just a single one, namely in the additive case 0, and this is the neutral element. Neutral means if I apply my operation, in this case plus, to this element and any other element, the other element remains unchanged. So the neutral element does nothing when I apply the operation. The other type is one where we have many of, namely for every element except 0, we also have, for every element in the group case, of course, we also have an inverse element. And this is simply, so this is a paired element for each element A, which has the property that if I apply my operation to both the element and its inverse, I get the neutral element, which is 0. I see some question marks here. The good news is if the question mark was for the stuff on top here, we don't care too much. This is something you naturally do when you compute. If the question mark was about these here, maybe a good way to clarify this is by taking a look at an example. First for addition and later for multiplication, then it will make more sense. So here's an example of the addition table modulo 11, meaning we're writing down what every element modulo 11 plus every other element modulo 11 gives as a result. And we see, for example, that adding 0 to anything doesn't change it, so we have identified our neutral element, it's 0. And we can now also go looking for inverses. So for example, which element do I have to add to 2 to get a 0? I can just look it up. I need to add a 9. So 9 is the additive inverse of 2. Because 9 plus 2 actually equals 11, which is the same as 0. Okay, so addition looks really easy. However, that's not what we're usually interested in. And it's also not what you're going to encounter in the exercises or in most of the schemes we're looking at. What you're going to see there is rather the multiplicative group. So instead of doing addition, we're interested in multiplying things. And the thing to notice is that if we look at the numbers we have so far and multiplication modulo n, then we will notice that it actually does not satisfy our requirements. Because the problem is that, for example, the number 0 has no multiplicative inverse. What this means is, if we take 0, then there is no other element that I can combine with it with my operation, so that I can multiply it with, to get as a result 1, which is the neutral element for multiplication. Because if I multiply anything with 1, it remains unchanged. Okay, so just taking modulo n and multiplication doesn't quite work out. However, we can easily fix this, and this fix is what is denoted by this star in the set here, or also here. So by adding a star here, what we mean is we take the numbers modulo n, however, we keep only those that also have a multiplicative inverse. So where this, so we only keep the a's where there exists an element b such that b times a equals 1. We have a visitor. Excellent. So for those bored in the mathematics because they already remembered, at least now you have a cat to look at. Okay, so let's have a look at the multiplication table, similar to the table we saw before. We can now already confirm here, for example, that the multiplicative element, the neutral element is 1, because we can see here, multiplying 1 to anything doesn't change this thing. Now, because it's a bit more interesting, let's look at one other row. For example, at the row of 2. So let's multiply 2 with everything. This is very easy up to 2 by 5 because nothing really happens. However, once we start multiplying 2 with 6, we get a result that is bigger than 11, namely 12, which means that we need to reduce it to match it back into our set. And what we get as a result is 1, because 12 modulo 11 is 1. And we see here that this continues, so 7 times 2, for example, is 14, modulo 11 equals 3, and so on. What we can also pick out here is what the multiplicative inverse of 2 is. So if I take 2 and look at the row where is the 1, which is our neutral element now, I can see that 6 is the modular inverse of 2. Now what's important is the notation that we use for this. So we denote the modular inverses like we would denote division for integers. So if we write 2 to the power of -1, what we mean is the inverse here. We do not mean 1/2 in the sense of 0.5. And this is something that already caused a bit of a confusion for some of you with the exercises. There are a few important concepts and names that we need related to this, or related to inverses. And some of these include the concept of coprimality. In German, this is usually called Relativprim. So two numbers are coprime if they have no common prime factor. So if there is no prime number that divides both a and b. And why is this concept relevant? It is because an element has only got a multiplicative inverse mod n if this element is coprime to the modulus. So for example, on the previous slide, 2 and 11 have no common prime factors because 2 is just 2 and 11 is just 11, which is a prime number. So this means that 2 must be invertible and that we must be able to find exactly 1, 1 here in this row, and thus the resulting inverse element. This is not the case if the numbers are not modular prime. So for example, if you would look for the inverse of 2 modulo 10, you wouldn't be able to find any, because both 2 and 10 are divisible by 2. And you will notice that all of the elements in the row here, if we did this modulo 10, they would all be multiples of 2, and there wouldn't be a single odd number, such as 1, inside the list. Okay, how do I find these inverses? Well, in the previous table, we just did it by brute force. We looked through the entire table until we found a 1. But if you implement this, then you need a clever algorithm to find one. And the one that you probably learned in discrete math is the extended Euclidean algorithm. If you dimly remember, this was this algorithm where you often wrote down a table which had rows A, B, R, and Q, and you did a number of steps until at some point you found a 0 and then you were done. The details really don't matter here, so you don't need to remember it. The important thing to know is that most computer algebra systems, or also many programming languages with integer libraries, already implement this. And you can find it under the name or under names similar to mod inverse or inverse mod or modular inverse, something like that. It's called a bit differently in each language, but you will find it under one of these names. Okay, there is one important function that is related to this, and that is the Euler phi function, which gives us, if we apply it to a number, it gives us the number of integers which are smaller than n and which are co-prime. So it counts how many numbers up to n do not have a common prime factor with n. This is quite easy to compute. So for example, if the number I'm using as an input to this function is a prime number, then I can know the prime number is certainly not divisible by other smaller numbers. So the number of relatively prime elements is going to be p minus 1, because all the p minus 1 numbers that are smaller than p are going to be relatively prime to our prime number. Very easy. And you can think for yourself what happens if you multiply more numbers. So for example, if you have an n which is the product of 2 prime numbers, then what will our Euler function, the phi function, give us as a result? The result is going to be p minus 1 times q minus 1, because which numbers have a common prime factor with p and q, with p times q? It's every number that is either a multiple of q, there are p minus 1 many of them, or it's a multiple of p, there are q minus 1 many of them. This is why we get as a result the number of relatively prime numbers is the product of p minus 1 times q minus 1. So as an example, if we take 15 as an input, this happens to be the product of 2 prime numbers, namely 3 and 5. Then the number of integers are, or the number of integers which are relatively prime is 3 minus 1 times 5 minus 1, which is 8. And if you take a look, you actually find exactly these numbers here, 1, 2, 4. So everything that's not a multiple of 3 and not a multiple of 5. Okay, that's a short recap on the Euler function and relatively prime numbers. And there is one important theorem related to this number, namely the so-called Euler theorem. And what this says is that for all integers and n's that are co-prime to each other, we learn that a to the power of phi of n equals 1 modulo n. Why is this theorem important? It actually has quite a number of applications. And one of them is for defining the generator, which we will need later. So what is a generator of one of our sets? It's any number such that it generates all other numbers as powers of itself. So what's a power of something? If we take an element a, and we look at a times a times a times a, and so on, up to some bound t, then we always get some other number. Very often these are going to be different from the first number, but at some time it has to start repeating. Why does it have to repeat? Well, if we compute modulo n, then we only have n numbers available. So if I do that many powers of something, I must start repeating a number at some point. And the interesting question is when I'm starting to repeat the entry 1. Why do I speak about repeating? Well, because for t equals 0, we already get 1 the first time. So anything to the power of 0 equals 1, if the anything is not 0. So this is the first time we hit 1. And the question is now, when is the next time that we hit 1 again in our list of powers? And if the smallest integer where we hit 1 again is exactly phi of n, then we say that A is a generator of Z. Because phi of n is the total number of numbers in this set here. If you remember, this set was the multiplicative group, which included all elements that have an inverse. And we just said that the elements that have an inverse there are exactly phi of n, many of them, which means that this set contains exactly phi of n elements. And if the smallest number to start repeating is phi of n, then I've generated all numbers. So I hope this was not too convoluted, this description. So let's have a look at an example with our small and convenient numbers. Namely, let's try to show that the number 2 we already had is actually a generator of Z11, meaning it generates all of the numbers in the list as powers of itself. And we need to test this criterion here, so whether 10, which is phi of 11, is the smallest number that we hit 1 again. So let's start. Let's start with 2 here. 2 to the power of 1 is 2 itself. That's rather boring. So let's exponentiate it. 2 to the power of 2, which is simply 2 times 2 equals 4. If we multiply 2 again, we get 8. Next we would get 16. But 16 modulo 11 is 5. And so on and so on and so on. I'm not doing all the steps here, but what we can see is that 2 to the 9 is 6 here. And 2 to the 10, which is 6 times 2, would be 12. But we saw 12 is equivalent to 1. So we jump from 6 back to 1. So exactly our 10th entry in the list is again the number 1. And we also see, we can check that we have visited all the numbers in the meantime. You will notice that the 0 on top here is missing. This is because 0 does not have an inverse modulo n. So it's not part of Zp star or Zn star. Okay, so 2 is apparently a generator. It can generate all the other numbers that are also invertible. And why is this generator number relevant, or why is this exponentiating relevant? It's one of the most central complexity theoretic problems that we use to build asymmetric Trapdoor. I see there is some question. Let's have a look. Doesn't this just depend on what mod you use? Yes, it absolutely depends on which modulus you use. So it's not a true statement to say 2 is a generator, period. However, it is a true statement to say that 2 is a generator of Z11 star. So it depends on the modulus. For example, if you take the modulus 10, then 2 would not be a generator. So you always have to say what it generates. And in this case, what it generates is Z11. So it's a generator of Z11. Okay, so we were speaking about the discrete logarithm problem. And this problem is the following. We have now seen that if we have a generator, we can generate all the other numbers as powers of it. And the discrete log problem now asks the inverse question. So it asks if we are given a generator and one of the any other numbers that it can generate, which is in this case called y, then the question is, how does my generator generate y? In other words, what exponent x do I have to pick So how often do I have to multiply g to itself in order to generate this element? This integer can be anything from 0 to p minus 1, or in other words, from 1 to p minus 1. That's essentially the same thing. Because anything larger will just lead to repeating values. So this is the choice of candidates I have, where p denotes the modulus now, because in the following we're only considering, for the most part, considering the modulus, which is a prime number. Okay, so this is the discrete logarithm problem. Given a generator, and of course the corresponding group, and given a challenge element that it generates, the question is, how does it generate? So what is the exponent I need to use to generate this element? And since logarithm is the inverse function of exponentiation, this is called the discrete logarithm problem. So how hard is this problem? It is hard, however, this hardness depends on the size of the set. So in particular, it depends on the size of p. And if p is a very large prime number, then we believe that this problem is secure. Why do we believe it? Well, you might remember from theoretical computer science that we have these complexity classes, and there are quite a number of very fundamental things we don't know. So in particular, one of the question is, are there actually something like hard problems that are easily verifiable? So for example, is NP actually different from P? One of the unsolved questions, where we believe that they are not equal, but we aren't sure. And similarly, we believe that this problem is hard because it has been analyzed for a very long time by very many mathematicians. And while the algorithms have gradually improved, there is no real breakthrough yet for the case where our modulus is a large prime number. I will come back a bit later to how large it should exactly be, because this defines what size of the keys gives us which security level in asymmetric cryptography. But for now, suffice to say, it's hard if p is large. Now let's have another example of trying to solve the discrete logarithm problem for a particular number. Let's take a similar example as before. So let's have again our generator 2 and our modulus 11. And let's look for a particular number, namely the number 10. And let's test for each possible exponent whether 2 to the power of this exponent gives us this particular number. So 2 to the 1, 2 to the 2, 2 to the 3 all don't work. 2 to the 4, which is 2 times 8, 16, which is the same as 5, also doesn't work. However, now we're getting closer. You already guessed that 5 times 2 equals 10, and 10 is actually 10 modulo 11. So this means that after the 5th step, we were successful, meaning that the discrete logarithm of 10 modulo 11 to base 2 is 5. So 5 is the answer to this challenge here. What we've seen here is already a very simple algorithm how to solve the discrete logarithm problem. What would be the expected complexity of finding the discrete logarithm this way? What we're doing here is essentially brute force. We're just trying potential exponents and testing whether they work. So if this were the fastest algorithm, then we could use security levels similar to symmetric cryptography. Because, for example, if I would have a 128-bit logarithm modulus, then I would on average take approximately 2 to the 128 steps to find the discrete logarithm, because the discrete logarithm is essentially in the same range as the modulus. However, unfortunately, this is by far not the fastest algorithms. So there are some significant speed-ups. There are some simple algorithms which give you a square root speed-up. This is similar to what we saw in the symmetric case for finding collisions, where we saw that for finding collisions we always had to double the key size, right? Or the output size. So for 128-bit security of a hash function, we needed 256 bits. And there are algorithms for finding the discrete logs, such as the baby step, giant step algorithm, which also have this speed up factor, because they're essentially based on finding collisions. This means that for security, we would also need to at least double the size, the bit size, to achieve a certain security level. However, it turns out this is not the best we can do. And actually, there are algorithms which are a lot faster, meaning they don't have this exponential runtime anymore that we have here, where we still need 2 to the 128, for example, for a 256-bit modulus, but where we can do something a lot faster, something that is sub-exponential. It's not exactly polynomial, but it's sub-exponential, which means that we need to increase our key sizes by quite a bit more than just a factor of 2. We need to increase it by a more than linear factor, the bit size. But I will get to specifics a bit later. So this is one of the most important hard problems. There's also another hard problem, namely the integer factorization problem that you might already have heard about. So the challenge here is you're given a number, and what you're supposed to do is you're supposed to factor this into prime numbers. You know that every integer can be written as a number, as a product of powers of prime numbers. And the challenge of integer factorization is to find this factorization. Or, in the minimal case, at least to find any two factors of n. Okay, so this is another hard problem, which is also believed to be hard, at least in one special case, namely in the case that n is not only large, but n also has to be the product of two large prime numbers. Why is it not sufficient for n to just be large? Well, there is always, if you take any very, very large number, there is always a very high probability that you have a very simple factor. For example, half of all huge numbers are divisible by 2. So for half of all very large numbers, finding a factorization is as easy as dividing it by 2. That's not very hard. But for the case where I have a large number, which is the product of two prime numbers, which are also both very large, then finding this P and Q is actually believed to be hard. So as an example, if you're given the input challenge n equals 143, then the challenge would be to find its prime factors, which in this case are 11 and 13. I see that there is a question popping up just in time before we finish the math part. And the question is, sorry for not being very readable, but I don't have a free slide now. Regarding the difficulty of problems, what is between exponential and polynomial? Actually, quite a lot of things are between exponential and polynomial. So the particular algorithms that we're talking about here, both for solving the IFP and for solving the DLP, so the two problems we saw, they are both sub-exponential but super polynomial. And there is a special notation that you can use to write down these numbers, and this is an exponential notation. So you write the class as e to the power of something, something that depends on n, so on my input size. Now if you write something like n in the exponent, so for example 2 to the power of n or so, this would be an exponential function. If you write 2 to the power of log n, this is similar to just having n. This would be a polynomial function. So you can rewrite any polynomial as 2 to the power of log of my number. And now if you look at a number to the power of something that depends on n, and you have neither just n nor just log n, but you mix the two, then you have something between exponential and polynomial. So if you look up any fast algorithms for solving these problems, such as for example the number field sieve or something like that for factorization, then you will usually find their runtime given in this notation. Usually it's written as e to the power of something log n and something n, where n is the number. If n is the size, then you have log n and log n instead. But this is what's between these classes. Okay, that's answered. Okay. I see something else here. That's something answered. Okay. Let's go back here. Now I need to hide the Q&A again. Why is it still here? There we go. Okay. We're almost ready for the break. It's already high time to do so. But first, a few introductory words about the first sort of scheme we're trying to build, namely key exchange schemes. We already saw the motivation for this, and right after the break, we're going to look at the first solution for this. It's a pity that the camera doesn't look down to the floor because Kat is having a lot of fun catching a fly, which you might hear occasionally. Okay, so what is this first solution? It's the so-called Diffie-Hellman key exchange protocol, which is like many innovations in cryptography from the 1970s. Okay, there's a lot of support for Kat. She hasn't actually managed to pin down the fly yet. Okay, so why is this encryption scheme so famous? Well, there are two reasons. First, it was actually the first asymmetric crypto system that was proposed. So it has had an extremely high innovation factor at the time. And the second reason is that it's also extremely versatile. So the general idea that they are using is the basis for a lot of other schemes. It can be translated to the elliptic curve case that you will see a tiny bit of in the exercises to make it a lot more efficient. It can be translated into signature schemes. It can be translated into many more advanced protocols in cryptography. So this Diffie-Hellman problem, which is the underlying problem here, is I think the single most important building block in asymmetric cryptography research. It was then and it still is now. So many of the ongoing publications and research items also deal with this thing, which is of course a very good reason to award it with the Turing Award, which happened in 2015. And the two guys who are responsible for building this construction are Whitfield Diffie and Martin Hellman. The scheme is also sometimes called the Diffie-Hellman-Merkle scheme. You might remember the name of Merkle from Merkle-Darmstadt, so he also did hashing. And this is because he also introduced for the first time the concept of asymmetric cryptography. So while he wasn't involved in this particular scheme, he was very much responsible for triggering research in asymmetric cryptography. So what is the goal again? We said that the key exchange scheme is needed because if we have more parties, we need quadratically many secret encryption keys prepared if everybody wants to talk to everybody. This means that if you look at the complete stack of what happens whenever we communicate, you will actually see three important steps. And the first of them, before you even start exchanging the key, first you usually want to authenticate to each other. So first you want to be sure who you're talking to. We can solve this with asymmetric cryptography, as we will see later. Then we need to agree on common key material, which is done by key agreement, which we're going to look at in a moment. Also asymmetric cryptography. So this is both parts of the initial handshake of the preparation. And then for the actual communication, we are going to resort to symmetric cryptography because it is simply so much more efficient. So for comparison, a classical number is that encrypting something with asymmetric cryptography, with RSA specifically, costs something like 1,000 times more than encrypting the same with symmetric cryptography. This is because, as we will see in a moment, the numbers that are involved are simply so much larger. You need to scale them up because of the sub-exponential runtime. And this makes the operation slow, and there are also several other factors involved. But before we dive into this, you have very much earned a break of something like 10 minutes, so I would suggest that we reconvene at 10:50, so in 10 minutes. And in the meantime, I hope you enjoy your well-deserved break. So here we go again, fresh after the break, and let's continue right where we stopped before the break started, namely with the Diffie-Hellman key exchange. So here is a schematic view of what we've seen so far. You will recognize Alice and Bob, right? But you will also see that now they're not just exchanging messages in one way, but back and forth. So what we're seeing here is an actual protocol. So how does this Diffie-Hellman protocol work? It starts by setting some system parameters. This is something that is not actually the job of Alice and Bob to do, but this is usually predefined. For example, it's written down in the NIST standard. And these system parameters are essentially defining in which group we are working. So in our case, this means we are defining a large prime number P, which so for our group ZP star, and we're choosing a generator alpha of this group. So these are predefined, they are not specific to Alice and Bob. Everybody in the world can use the same parameters. But what is up to Bob and Alice to choose? Well, both of them start by choosing a random number, somewhere in the range from 2 to p minus 2. Alice calls her number A, Bob calls his number B, and these will serve as the secret or private keys of Alice and Bob. What do they do with it? Well, what Alice does is she takes the exponent alpha and raises it to the power A. So public exponent to public basis, and her private exponent. And she does this modular P, of course. And Bob does exactly the same thing with his secret number. He takes the public generator alpha and raises it to the power of his secret exponent. And both send each other these resulting numbers, which are also serving as their public keys. So this is Alice's private key, and this is Alice's public key. In our example, she's just sending it to Bob, but she could also publish it globally. And Bob, exactly the same case. Now both of them have received each other's public keys, and they can do some computation with it. Remember, the goal is that they are trying to derive the same symmetric session key that they can use. And Alice does this as follows. She takes the number she has received from Bob, which is equal to alpha to the B, but Alice doesn't know B. She just knows the result. What she can do with it is she raises it to the power of her own exponent, A. And Bob does the same thing, so he takes the number he has received from Alice and raises it to his secret exponent. And now the magic idea, or the magic thing, is that these two resulting numbers are actually the same. So, this has fallen asleep because I'm in the wrong window. So why does this work? If we look at what Alice and Bob compute, we can see that alpha to the B to the A is actually, according to the usual exponentiation rules, the same as if I take the two exponents and multiply them. So this is a simple exponentiation rule that you know from school, essentially. And in multiplication, the order of elements doesn't matter, so I can simply swap them. But now I have the same pattern as here, and I can transform it back to say that this is the same as first raising alpha to the power A, and then raising it as to the power B, which is exactly what Bob computed. So we see here that Alice and Bob computed exactly the same number, but they did it in different ways. The one took the other's public, so Alice took Bob's public key and raised it with her secret key, and Bob did it the other way around. But both of them give us exactly the same result. Let's have a quick example of numbers to put to it. So let's say our super large prime is 11. Again, you already know that one. And our lovely generator is 2, which we also know from before. Now Alice picks a random number between 2 and 9. Let's say it's 3. So she computes 2 to the power of 3, which equals 8. Bob also picks a random number in the same range. Let's say he picks 5. we already computed earlier that 2 to the power of 5 is the same thing as 10. So it was like 2, 4, 8, 5, 10. Those were the powers of 2. And they send each other this resulting number, but of course not their secret key that they chose. And let's verify that the property we showed in the previous slide holds. So in case of Alice, she receives a 10 from Bob and raises it to the power of 3. 10 to the 3, as you know, is 1000. What you don't see immediately, but what you can find out by taking out your calculator, is that 1000 modulo 11 turns out to be exactly 10. For Bob's side, something different happens, but we get the same result. So Bob takes the 8 he has received, computes 8 to the power of 5, which is some large number, which you can verify if you want to use your calculator. You can also verify that this large number modulo 11 equals 10. And this is exactly the same result that Alice got. So the functional part seems to work out. Now, of course, the question is, what about the security part? Why on earth would this be secure if they send each other all those numbers? And let's first define what security actually means and what functionality also means. So to recall, we had these public parameters p and alpha, and we had the public keys alpha to the a and alpha to the b. Security now means that given all this information, the public system information as well as the public keys, Eve, if you remember that was our adversary, Eve should be unable to derive the secret key that both Alice and Bob agreed on. So to do that, what you would need to learn is the number alpha to the a times b. And this is what you should be unable to do. We also call this the Diffie-Hellman problem because it's the essential security problem of this scheme. And it says that exactly what we said above, given the public system parameters alpha and p, and given the two public keys, the challenge is to find the resulting alpha to the a times b. And what people believe is that this Diffie-Hellman problem is as hard as the discrete logarithm problem, because the fastest way that we know how to solve this problem is by trying to take one of the public keys and recovering the secret exponent from it. If you remember, this is exactly what the discrete logarithm problem was about. And this is the fastest way we know for solving this. So if we can solve the discrete logarithm problem, we can, for example, take alpha to the b as an adversary, recover b from it, take the other public key we know and raise it to power b. So once we've recovered one of the secret keys from the public keys, we have won. And this is, it's not known whether this is exactly equivalent, but it seems to be the best way of approaching this. So what does this mean for the key sizes? It means that solving the discrete logarithm problem in this particular group should be a hard problem. And we already said that the algorithms for solving the DLP have sub-exponential runtime, which means if we want to have 128 bits of security, we're going to need way more than just 128 or even 256 bits of key size or of modulus size here, because the modulus defines us what the number of candidates for the discrete logarithm is. And so the current best estimate is that for 128 bit security, judging from the current algorithms we know for solving the DLP, something like 3072 bits should provide approximately this security level. If you try to look this up online, you will sometimes find numbers like 4096 instead of 3072, but somewhere in this area is a good answer for providing at least 128 bits of security. I see that there is a question, so let's have a look at that. Are the stick figures in the diagrams from XKCD comics? Yes, that is well observed. So these are, I think, Megan and I forgot. I think he's called Harry, if I remember correctly. So yes, they are from XKCD. However, they're included here. So I've vectorized them and then translated them to TIX code. So they're actually coded in LaTeX here, these figures. Anyways, okay, so back to the content. Let's hide the Q&A again. And let's continue with our protocol here. So we were talking about the security, and we were saying that the security level, for 128-bit security level, we need approximately 3000 bits of key, which is quite a lot. It means that we need to do all of these operations with really huge integers. And this also means, of course, that the exponents that we have here can also be pretty huge. And you can imagine that exponentiating by such a large number, even if you do it in an efficient way, for example, with square and multiply, this is going to take a lot of operations on your CPU. So it's so much slower than AES that it's really hard to compare. Okay, but this is the most basic building block and the first approach how you can agree with your partner on key material to use with AES, for example. But we said that there's also a second approach, namely by just sending the encrypted key using asymmetric encryption. And the the primitives that we use inside asymmetric encryption can also be described as follows. So it can be described as a so-called trapdoor one-way function. What does it mean? Let's first analyze the last part. So let's go from back to forth. So what we're needing is a function, and it's supposed to be a one-way function. You may remember this term from hash functions, but you will see that we're not talking about exactly the same thing. What is similar to hash functions is that they should be easy to compute in the forward direction, which corresponds to locking such a padlock, for example, and it should be hard to invert. So easy to compute from input to output, but hard to get back from the output to the input. It should be hard to open. So up to here, this describes a one-way function, but what we need specifically in asymmetric cryptography is a trapdoor one-way function, which means it is hard to invert, it is hard to open, unless you know the trapdoor information. So the secret access, or the key, the secret key, which allows you to open something even though it's hard for everybody else. So very similar to a padlock, everybody can lock it. You cannot unlock it unless you have the key. And the key is this trapdoor information. And the idea is that you would send, so that everybody can send something to you by locking it. So you could distribute open locks and everybody could put the lock on something and close it, but only you can open it afterwards if you have the key. And these processes are usually described instead as a set of 3 algorithms. And the first of these algorithms is, so now we're talking within asymmetric encryption, there are these steps, and the first step or the first algorithm you need to implement is key generation. So generating the parameters and the private and public key that you're going to use later, like setting up the clocks, the padlocks. So for key generation, in our case, Alice is the owner of the secret key, of the private key. So she will need to generate her private key and also to derive the corresponding public key. I'm representing this here by a key symbol in the cloud because the idea is that it is the key material, but it's public. So it can be put out in the cloud, for example. And after this key generation is done, she distributes the public key publicly and keeps her private key safely somewhere. So this is the first algorithm that needs to be defined when you define an asymmetric encryption scheme. You will notice that we never really defined this process for symmetric crypto. And this is because the process is so simple for symmetric crypto. You just need to come up with a random bit string. That's it. No additional things attached. You don't need to look out for any special properties, it just needs to be a few random bits, that's it. And in asymmetric cryptography, this is unfortunately a lot more complicated and a lot more can go wrong when you do it. So we have put it in a separate algorithm. Next, of course, I want to do something with my key, namely I want to encrypt something. And who wants to do this? Well, anybody can. So Bob can, but also everybody else. And to do this, they take the public key and put it into the encryption algorithm together with the message to produce the ciphertext. We use a similar notation as in the symmetric case, so we write the encryption scheme with a calligraphic E, where the encryption key is the public key and the input is the message and the output is the ciphertext. And the ciphertext can then be sent to Alice. There is a question, namely Electra easy just generate a random bit string. Deterministic computer, well, I agree on that. The good thing is not all circuits that you can build are entirely deterministic, and there are quite a number of noise sources that you can sample something from. I will go back a bit to this problem of generating random key material in the next lecture. Okay, but it's still, you're going to see, it's a lot easier to generate 128 random bits than to generate the stuff you need for RSA. Okay, so that's the encryption part, and of course if we can encrypt, we also need a decryption algorithm. And this is what Alice here executes. So when she receives the ciphertext, she plugs it into the decryption algorithm together with her private key and recovers back the message. Now it's again time for some photos of important people, namely our important people R, S, and A, Ron Rivest, Adi Shamir, and Leonard Eilman, who are the inventors of the RSA encryption scheme and the namesakes, of course. If you look at the date, you will see that this is very close to the genesis date of Diffie-Hellman key exchange. It's just 1 year later. So very quickly after this idea of asymmetric cryptography was born by Ralph Merkle, if you remember. We first had this key exchange scheme, and very soon after this encryption scheme. It also received the Turing Award quite a bit earlier than the Diffie-Hellman scheme, namely in 2002. So if you follow cryptographic literature, you will see that Ron Rivest also invented quite a number of other things, including some hash functions. And Adi Shamir is generally extremely active and is also responsible for some of the most important cryptanalysis techniques, for example, in symmetric cryptography, as well as things like side channel fault attacks and so on. So he's really active in approximately everything. He focused more on a mathematical career and didn't do so much cryptography afterwards. Okay, so these are the guys who who gave us this wonderful encryption scheme. To explain it, we do need a few things from before the break, and I've written it down here on top so that you can remember more easily. So we need first the definition of the Euler function you have on top here. If you remember, the Euler function of something was the number of relatively prime numbers to this input. And if we put a product of two prime numbers, p and q, inside, then the result is going to be p minus 1 times q minus 1. And we also had a look briefly at the Euler theorem, which says that if two numbers are co-prime, then one of them raised to phi of the other one always gives us 1 modulo the second number n here. This property, if you didn't think about it earlier, think of it again in terms of the definition of a generator we said, then this property will make more sense. And this theorem has a number of applications, and one of them is going to be right here for key generation. So how does it work? I promised it's going to be more difficult than just generating 128 random bits. And the first reason why it's more complicated is because the very first thing to do is we need to generate not one but two numbers, p and q, which are both quite a lot larger than 128 bits. They are, like in the Diffie-Hellman case, more in the area of 3,000 something bits each. And they not only need to be random numbers, they need to be prime numbers. So you need to verify this during the key generation, that the numbers you picked are actually prime numbers. Okay, and of course you need to keep them secret, just like an AES key. What you do not need to keep secret is the corresponding public key. This public key is the product of my two random prime numbers I generated, and we call it n. It's going to serve as our modulus. So you will notice that before we had one prime number, it was public and it was our modulus, and now we have two prime numbers, they are private, and their product is the public modulus. In addition to that, we are going to need to generate even more random or non-random stuff. Namely, we need to choose a public exponent, which is called e, and which must be relatively prime to phi of n. We will get in a moment to why this is a necessary condition. So notice it's not relatively prime to n, but it's relatively prime to phi of n. What's good here is that this number doesn't actually need to be random. You can also just pick something like 17. So it doesn't contribute to the security if this is a known number. And one of the most frequently used numbers is 65,000 something. From this, however, we derive another secret number, namely the secret exponent. So we have a public exponent and a secret exponent, which is the modular inverse of our public exponent. Not modulo n, but modulo phi of n. Notice that this is different from what we've done so far. Now, why are we computing modulo phi of n here? This is because I've been hinting already that we're computing in the exponent, and part of the reason why RSA works is if you're looking at computations and you're computing modulo n, and then you do some computations in the exponent, then you can do all the exponents, the computations up there modulo phi of n. The reason for this is Euler's theorem, but I will be more specific in a second. Anyway, all the blue numbers are now our public key, so both the modulus and the public exponent are public, and what's private is everything else. So in particular, D is private and P and Q are private. Don't be confused that I'm listing both D and N here as part of the private key. N is of course also part of the public key, so this is not a secret number. However, Alice needs to know both D and N. She doesn't actually need to know E, which is why I've not listed it here, but she needs to know the private D and the public N. Okay, so this is our much more complicated key generation process right there. Now, of course, we don't have a lot of room on the slides left for defining the actual encryption and decryption. The good news is they're so simple that they still fit. So what's the encryption mechanism of RSA? You take the message you want to encrypt, and then you take your public exponent from up there. Remember that everybody can encrypt, and you simply raise the message to the power of the public exponent modulo n. The result is the ciphertext. That's it. So it's a lot easier to write down than something like AES, where you need to define the round function, blah, blah, blah. Here it's just an exponentiation. However, being simple to write down, of course, doesn't mean that it's simple to evaluate. Because like before, this is going to be a 3000-bit number, this is going to be a 3000-bit number, the exponent is going to be a 3000-bit number. Wow, okay, so that takes a lot of iterations to actually evaluate that. So mathematically simple to write down, a lot messier to actually execute. That leaves us with the missing decryption function, which looks just as simple as the encryption function. Namely, it's essentially the same, except you take the ciphertext instead of the plain text. You take the private exponent instead of the public exponent, but you also raise it modulo n. And why exactly do you get back the original message n? Now this is where the Euler theorem comes in. Because Look at the expression we have here. Ciphertext to the power of the secret exponent. If you remember how the ciphertext was defined, it was m to the power of e. So in total, if you expand this, you get m to the power of e times d by the same exponentiation rules we saw before. Now, how were e and d chosen, if you remember up here? We said that the two are multiplicative inverses to each other, modulo phi of n. Now that's a lot of words to just say that if you multiply the two, what you get is 1 modulo phi of n. So 1 plus some multiple of phi of n. And because of the Euler theorem, if we expand this, we get m to the power of 1 times m to the power of this thing here. However, m to the power of phi of n is 1 because of this property here, which means that this entire part simply disappears. It evaluates to 1. And everything that's left is m to the 1 plus 0 in the exponent, or times 1 in total, which is exactly m. So this Euler theorem here is responsible for the fact that we can do all the computations in the exponent modulo m, because the contribution of modulo phi of n, because the contribution of phi of n will simply disappear, because m to the phi of n is 1. And k times phi of n is 1 to the k, which is still 1. And this was the reason why we chose these as multiplicative inverses, so that they multiply up to this one here. And this is why the functional correctness of RSA is given. So why decryption is the actual inverse of encryption. Let's have a look at an example with numbers. So instead of two huge prime numbers, of course, we're going to pick two tiny prime numbers. And our modulus is the product of the two. We choose a random public exponent, which needn't really be random, we just pick 3. We will now need the Euler function, so the phi function of n, to do some of our next computations. So we compute that. So phi of 33 is phi, so it's p minus 1 times q minus 1, 2 times 10, 20. And now we need to derive the private exponent. This is the modular inverse of 3 modulo 20. So now we're looking for a number such that this number times 3 equals 1 modulo 20. And this number turns out to be 7. Why? Because 7 times 3 equals 21. And 21 modulo 20 is 1. So 3 and 7 are inverses to each other. And 7 is our private exponent. Let's do some trial encryption. So let's encrypt 4. So 4 to the power of the public exponent, so 4 to the 3, turns out to be 31. Ask your calculator about it, at least if you do it modulo 33. For the decryption, actually you don't need your calculator for this. So 4 to the 3 is the same as 2 to the power of 6, which is 64, and 64 minus 33 is 31. Okay, so without calculators. Let's decrypt it back. So ciphertext would here be 31. Let's look at the decryption. Ciphertext to the power of our secret exponent equals 33 to the power of 7. Now you do really need your calculator probably, or at least I would. Anyway, the result is going to be 4 modulo 33. So with tiny numbers this is reasonably easy, but as you can imagine, with large numbers come large difficulties. What about the security of this scheme? What is it based on? So we were talking a lot about secret exponents. However, RSA is, or the RSA problem is not actually usually phrased as a discrete logarithm problem, as you might expect from this here, because we do have a secret exponent. And one of the reasons why it's not a case of the discrete logarithm problem, or it doesn't directly work as a comparison, is that the thing we're trying to find out in the RSA problem is not the exponent, but we're trying to find the message that was raised to the public exponent to get the ciphertext. And one of the other reasons why this isn't quite a match is, look at the modulus here. We're not computing modulo a prime number, which means we're also not really computing in the same type of group that we saw before. What this problem is instead related to is the integer factorization problem. This is because the modulus was the product of two prime numbers. And if we can find the two prime numbers from the modulus, then we can do all the computations that Alice can do. So in particular, if we do learn the prime numbers p and q, we can find phi of n, and with this we can recover the secret exponent. And the situation is actually quite similar to Diffie-Hellman problem versus discrete log problem. Here we also believe that the RSA problem is as hard as the integer factorization problem, and the integer factorization problem in turn is believed to be hard for large n, which is the product of two suitable primes. You will notice that on the one hand there are a lot of if and whens and assumptions in there, and on the other hand there's something I didn't notice here, namely there are a lot of cases where factoring is easier than it should be. So there are many properties of the prime numbers that are unfortunate and make the attacker's job easier. Some of these properties include, for example, if the two prime numbers are too close together, or if they are way too far apart, or if they're a particular type of prime number, or. So there is a huge list of exceptions, in which case the RSA problem is not as hard as we would like, and it's a lot easier. So when you generate the RSA key, in addition to the stuff I listed here, which is already complicated enough, you will also have to check for many properties that the prime numbers should satisfy. And this of course means that an implementer of this needs to have a lot of knowledge to be able to securely generate numbers. And this unfortunately goes wrong from time to time. So quite often we, or too often, not very often, but too often we read stuff in the news. So for example, a year or two ago, there was some news that the prime generation on some smart cards was buggy, and that they didn't check for some of the properties that they should check, and for the reason the result was a bit biased and could be attacked. So this is a very delicate process, and one of the reasons why RSA isn't used that much anymore. Before we go to the rest of the slide, I see that there have been quite a number of questions. So let's have a look. Let's start with the question that appeared on Menti. How does one quickly find the inverse of E in RSA? The simplest algorithm to do this is the extended Euclidean algorithm, which you learned in discrete mathematics. It consists of a number of divisions and multiplications and subtractions, so some simple steps, and it gives you the inverse reasonably quickly. It's still not extremely fast, so it is a costly process, but it's okay. It's acceptable for the parameters we usually have. And if you just want to actually know one of these inverses and are not interested in implementing this extended Euclidean algorithm, then you can simply go to your favorite programming language, which has some integer library, and ask it to do something like mod inverse or inverse mod. This is usually the name of an implementation of one of these inversion algorithms. There are also other ways besides the very simple extended Euclidean algorithm, and quite a number of optimizations, but I'm not really planning to go into the details of this. Suffice to say, there are efficient algorithms to find it. Actually, these algorithms, in particular the Euclidean algorithm, if I remember correctly, was one of the first algorithms that ever had a solid complexity analysis done for it. So one of the first examples where people try to analyze the number of steps it takes. Okay, then There were also a number of questions on in the YouTube chat, so let's have a look. Blah, 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 blah. So on the previous slide it said e to the -1 mod. How does mod handle float? There are absolutely no floats involved here at any point. None of the numbers here are ever floats, and the inverse computation also does not include any floats. It simply finds another integer that satisfies the property that d times e equals 1 modulo something. And if you remember back to the first half of the lecture, we did find this inverse by simply looking at the multiplication table. Now for real large numbers, of course, you can't set up the implementation tables, but you can still have efficient algorithms for computing the extended Euclidean algorithm. Okay, what other numbers questions do we have here? Blah, blah, blah. All integers, always has been, yes. Blah, blah, blah. Okay, e is not the Euler number. That's maybe an important point for the explanation here. So e is just the number of the name of an integer we pick here. For example, 3 or something else. So again, to clarify, at no point in any of these implementations will you find a floating point number. All integers. And the same also holds for the Diffie-Hellman problem. In general, floats are something that you usually don't find at all when implementing cryptography. Neither in asymmetric cryptography nor in symmetric cryptography. There are a few exceptions, but you will probably never encounter them. So you do get floats in the analysis, of course, and there are also some schemes that work a bit like that, but you're very, very unlikely to ever encounter a float when you look at a cryptographic implementation. What? Do I have an IQ of 197? Despite what Trump claims, you can attack other people's stuff and do cryptanalysis without knowing 15% of their password or having an IQ of 197. Okay, so I have no clue where he got that from. Actually, that's a very good point to bring this up, because as a small side anecdote, referring to Trump's quote of needing to know 15% of some password, actually many of the asymmetric schemes have the very interesting property that if you do know a certain percentage of the key, you can recover the rest. So in case of RSA, for example, if by some means you learn 25% of the keys involved here, of the secret keys, you can recover the rest efficiently. This is completely counterintuitive, because after we've learned 25% of the key, there is still something like 2000 and something bits left. However, by doing magic math, you can recover them efficiently. But I don't think Trump was referring to that in his quote. Anyway, okay, so back to security of RSA. A few more comments on this. So, of course, again, the number of the modulus, as we've mentioned already, needs to be large. And it needs to be so large that the best factoring algorithms aren't feasible for an adversary. To give you some examples about these sizes, as far as I'm aware, one of the most recent factoring records was back in 2009, and the number factored at that time was 768 bits long. This is interesting because when RSA was first proposed, the factoring or our knowledge of factoring algorithms was quite a bit worse. So at the time it was actually estimated that 512 bits should be secure. Now this factoring record clearly shows that 512 bits are not secure. You rather want something in the same area of Diffie-Hellman, which is approximately 3000 bits. For your information, this particular record here took about 2000 CPU years. But of course, single core CPU years, and this was parallelized. So here, similar to Diffie-Hellman, it's very important to notice that the key size is not the same as the security level. So of course the key size defines the security level, but the key must be a lot larger than our security level. So for example, for 128-bit security, the key size, so the size of each prime number, should be over 3000 bits. If you look around in practice, you will find that most RSA keys that are currently used are 2000, 3000 or 4000 bits. If you do at some point run into key sizes of 1000 bits or less, please make sure that this is updated, replaced, whatever. It's probably a very outdated number or taken from some a very outdated documentation or default value. 1000-bit keys are no longer recommended as secure. There are more questions, including, can you give a keyword I can search up for recovering the remaining 75% of the password? I think you may want to search for something like bit hardness of RSA. So this is a related word. Or you simply try something simple like recovering RSA key after knowing part of the key. But a warning ahead, it's a bit complicated, so you will require some reading. Daniel has the name of the attack for you. Coppersmith's attack. Okay, a few more comments on the security of RSA. Namely, what we've explained so far is what we also call textbook RSA. And the bad news is that if you just use textbook RSA as is, even with secure primes and secure key sizes, you're still in trouble. And why is that? The main problem that we have is one that we already saw in symmetric cryptography, namely that the encryption scheme we defined is completely deterministic, meaning same input, same output. So this is particularly relevant in this case, or even more dangerous than in symmetric cryptography, because the attacker always has access to the encryption oracle. The attacker can encrypt as much as they like because they have access to the encryption key. And for example, if the attacker knows that the message that was sent, that they want to learn from the ciphertext, was one of a small set. For example, the message was either yes or no or maybe. Then what the attacker can do is they can do a trial encryption. So use the public encryption key, encrypt the message with it, and see whether it matches the ciphertext they want to decipher. So the one they intercepted. And if it matches, it must have been because it's the same input. And it will match because the scheme is deterministic. So this is a huge problem. And what we want to have instead of this deterministic encryption is we want to have an encryption scheme that is what we call semantically secure, meaning this should no longer work. And to do this, we need essentially, like before, a mode of operation. In this case, the mode of operation is simply called a padding scheme. This is because we don't really need to encrypt arbitrary length messages anyways, and we don't need to do anything in addition. We just need to have an additional input that randomizes my encryption process. And the goal is that we achieve this security notion here. The name is not very catchy. It's called indistinguishability under adaptive chosen ciphertext attacks. No need to learn this name by heart, but it's important to understand the concept. So what this notion means, which also implies our semantic security here, is that assume we have an attacker who knows, of course, the public key, and the attacker is allowed to choose a set of two messages. So like our yes or no or maybe here. And what the attacker receives is the encryption of either message 0 or message 1. Then it must be impossible for the attacker to distinguish which of the two messages is encrypted in the ciphertext. So in other words, exactly what we described here, exactly this is impossible. And this should be impossible even if the attacker has some additional skills, for example, even if they can ask a decryption oracle for decryption of any other ciphertext except the challenge ciphertext. Okay, so this is the notion we want to achieve, and we need some sort of randomization. Because if we stick to the deterministic textbook RSA, same message is always going to be same ciphertext, and the attacker can simply compare. So we need some padding scheme. The good news is there are several, and one of them is simple. The bad news is the simple scheme is broken. So for this reason, I'm showing both of the schemes, but please don't learn them by heart. It's just that you know the general concept. So the first padding scheme I'm listing here is also called PKCS number 1. Yay, another acronym. This one stands for Public Key Cryptography Standard. And this is a standard that defines both of the schemes we're interested in. And the name that the standard has for this type of scheme is RSA encryption schemes. You will recognize the scheme word that we also used in symmetric cryptography. Defines the final product that you should use. So you don't use just plain AES or plain RSA, but you use it in a mode to get a scheme. So in particular, even though it says AES here in this name, this hasn't anything to do with AES, it's just RSA encryption scheme. And the first one of them, which is simple but broken, or deprecated at least, is the RSA-AES PKCS1 version 1.5 padding scheme. It's very simple. So if you want to encrypt some message M, which is not quite as long as the modulus, what you do is the following. You simply prepend a 0 to separate it from a random byte string that you add. Now the only requirements for this byte string are it should be at least 8 bytes long to have enough randomness, and it doesn't contain any zeros, so that this delimiter here really works. And additionally, you write some numbers in front here that denote that it's this padding scheme. And so you take your padded message and simply plug this padded message into textbook RSA. And the random bytes here will serve as a randomization, so that even when you encrypt yes twice, you will do it with different random numbers and get different results. So these random bytes here play the same role as the nonce in symmetric encryption schemes. That's a simple scheme. I'm showing briefly a picture of the complicated scheme. This is called RSA-AES OAEP, where OAEP is optimal asymmetric encryption padding. And it does a bit more than just adding randomness. So it does have the randomness and it does have the original message, but in addition to just concatenating them, it does some hashing, but some strange hashing with different output sizes. So it expands this random seed to a larger value to add here, and then expands this again to a value to add here. And in the end, you have masked this original seed based on the right hand side, and you have masked the original message based on the random seed, and the result is what you plug into the RSA scheme. So it's like a more complicated version of this with some hashing going on in addition. And these are usually the schemes you can choose when you choose to use RSA for encryption, or more specifically for transporting your keys. And if you have the choice, pick that one. Okay, that leads us to the very last part and the primitive that we are still missing. And those are signatures. So far we've been only talking about authenticity. Now it's time, only about confidentiality. Now it's time to get back to authenticity. The good news is we don't have a lot of time left, but we will still be able to cover that because we can reuse exactly the building blocks we saw already to solve this. Let's turn off the light a little because you do begin to see my wall here, unfortunately. Okay, so we again have several algorithms in these schemes. And we again start with a key generation algorithm, where we again generate a private key, a public key, and distribute them. Alice is again our owner of the private key. This time she's not going to be the recipient of the messages, but the sender, because the sender is the person who performs, so who adds the authentication to the message. And this process is called signing. So what Alice does is she takes her private key and the message, plugs it into the signature algorithm, and will receive a signature, which is similar to a MAC tag or a hash output. I denote it by this stamp symbol here. And she sends this signature or stamp together with the original plaintext and passes it on to the recipients. And the counterpart for the signing algorithm is the verification algorithm, which involves the public key, and anybody who receives the message and the signature can put the message plus the signature into the verification algorithm and gets as an answer either yes or no. I just see that there's a typo here, so the signature is called signature and not tag, so this should be an S. I'll fix it in the uploaded slides. And again, Alice is the one who adds the signature, and everybody who has the public key can verify the signature. So here is again our usual stick figure picture, which will remind you a lot of the picture that we had for Macs. The big difference here is that the parties don't have the same key but have their different keys. So what does such a signature scheme provide? Which security properties? First of all, it authenticates the sender. So you have a guarantee who sent the message. Second, it also guarantees message integrity, meaning if the signature verifies correctly, you also know that the message has not been changed in transit. And third, you have non-repudiation, meaning that Alice cannot deny at any later point that she has sent this signed message. So if she signed a contract or something, she won't be able to deny this later on, because nobody except her has the private key. What are the security notions that we have here? So the concept is very similar to the trapdoor functions we heard before. It must again be easy to compute the signature if you know the private key, but very hard to do it if you don't know the private key. And computing a correct signature without knowing the key is again called forgery, like for Macs. And on the other hand, it must always be easy to verify the correctness of the signature. And again, we're going to be, so we can build signature schemes from both of the problems we saw so far. And I want to briefly show how it works with the integer factorization problem. In the exercises, you will deal with how to do it from the Diffie-Hellman problem, so from the DLP problem. So this signature scheme has the same age as the encryption scheme, and you will notice that the slide also looks almost exactly the same, because we have exactly the same ingredients. We have precisely the same key generation process as before. You will also find the signature scheme very familiar because it looks exactly like the previous decryption. So to sign something, you simply take the message you want to sign and exponentiate it with your secret key. The result is the signature. So in particular, you notice that the signature will have the same size as the message, namely the size of the modulus. And the verification looks exactly like the previous encryption functionality, meaning that whoever wants to verify that the message and the signature fit simply takes the signature, exponentiates it with the publicly available key, meaning everybody can do this, and checks whether the result matches the message. The reason why this works functionally is exactly the same as for RSA encryption. You simply decrypt your message to sign it and encrypt your message to encrypt your signature to verify it. Some notes on the security. We have very similar remarks as we had for RSA encryption. And one thing that you will notice in particular, if you see the similarity with the RSA encryption mechanism, you will notice that if you have the signature, you can actually recover the message from the signature, which is absolutely not a feature that you need in a signature scheme. So usually, if you remember MACs, you weren't able to recover the message from the MAC. This is not something that should be possible. In particular, it would actually allow attacks, because if an attacker can simply come up with any signature and then apply this step here to recover a matching message, then they would have forged a valid combination of message and signature. This should absolutely not be possible. Which means, again, we need some fixing to remove this property. And this fixing will contain two steps. The first step is at the same time functionally necessary, because we've said so far message and signature have the same size, which means the size of the messages I can sign is very limited. It's limited by the size of the modulus. This is of course a very bad idea. We want to be able to sign large messages. So we need a way to compress our messages first. And how do we compress stuff? We plug it into a hash function. So whenever you see a signature scheme used somewhere, this is always a so-called signature scheme with appendix, which means what was done to sign the message is that first the message is hashed to have a short fingerprint of the message, and then only this fingerprint is put into the actual signature algorithm. And again, you need to be careful how exactly you do this, which is why there is again a scheme defined by our lovely PKCS number 1 standard, which is called, so the type of scheme is called RSA SSA, for RSA signature scheme with appendix. And it looks as follows. So the simple version is again the version 1.5, which consists of hashing the message. This is something we would do anyway. And then just adding a particular padding. So a 0, then we don't really need randomness here. This is just a fixed string of f's that is long enough to fill up the size of the hash to the size of the RSA. So this means that this part here is actually quite long. Why? Because we said that a secure hash function has a 256-bit output, but a secure RSA modulus is 3000 bits long, which means this part here will be approximately 2800 bits long, full of ones. Now this is what we plug in the signature scheme. Again, there's a more complicated version which does randomize a bit. So it's called RSA SSA PSS. Cryptographers and standard writers just love acronyms. PSS is for probabilistic signature scheme. And again, if you have the choice, this is the one you pick. Okay, that leads me to the conclusion for today. So what did we see? We first saw that when you actually try to communicate with someone, to build up communication, you do 3 steps. You first authenticate to each other. You can do this by showing a certificate with signatures. We will see that next week. So the details of the certificate stuff. What you can also do is, what you also do next is you agree on a session key, on a symmetric session key, by using, for example, Diffie-Hellman key exchange or encrypting your AES key with RSA. And then you do the actual communication. This you do with symmetric cryptography, like AES GCM, for example, using the session key you've agreed on here. And we've seen 3 very important asymmetric schemes today. All of them need a key size of approximately 3000 bits. We saw Diffie-Hellman key exchange, RSA encryption, and RSA signatures. And what you see in the exercises is a signature scheme that is based on Diffie-Hellman key exchange. So you will see the same building blocks. You will see the public generator, the secret exponent, but with a few more messages around it. What you also see in the exercises is that the data type of the values inside the Diffie-Hellman scheme changes. Namely, instead of working with integers, we work with points which have an x and a y coordinate. But you will get an explanation about that the essential ideas are all exactly the same. So that gives us a bit of time for questions. As usual, I first have a question for you, namely to just recap what we've done so far. This is actually something I wanted to do after the break, so it's a bit late now. But anyway, maybe you have some new concept that you've learned today. If so, it would be great if you could list it now, so that we can refresh a bit all the stuff we've heard today. Looks here like you're all a bit reluctant today, but here are the first few answers. So some of them, some of you found the actual schemes we saw new. Some of you were fascinated by the concept of there being something between exponential and polynomial. The modular arithmetic recap was at least new to some of you. Some of you managed to actually remember the acronyms RSA, ES, OAEP. Very good. Good short-term memory. And RSA, SSA. What else do I see here? Modular inverses. Yeah, please don't forget those. You will encounter them a few more times, and people keep finding them very confusing because they always expect getting a float instead of an integer. What else do I see here? Discrete log scheme. Yeah, very important problem that you will see very often also in modern schemes, in more recent schemes. The phi function. What else do I see here? Weirdly named paddings. Yes, that's definitely a feature of today's lecture. Anything else? The decryption process of RSA. The trapdoor one-way function concept. Yeah, that's actually a really good generalization that also applies to other encryption schemes that we have. And it also just captures the idea of asymmetric encryption in a clear image. Congruent modulo n. Yes, so some vocabulary from the math part was apparently good to repeat. Okay, I guess that's already a very, very good summary of many terms from today. Again, I'm particularly impressed with the people who remembered the acronyms. Of course, you don't need to do that for the exams. So RSA, yes, but not PKCS1, OAEP, whatever. So this was one question from me to you. I think I have another one. Yeah, so this is a bit to put into context all the primitives we've heard so far. So it would be great if you could rank what you believe from all of these schemes listed here, what are the most secure. So the most secure one should be on top and the least secure one should be on the bottom. And I've picked here different schemes from the last 3 lectures and given some key sizes that were used for these at some point in time. Not all of them are up to date. So please think what you can remember and how you would judge them. So what do we have? So apparently most of you agree that MD5 is a bad idea no matter the exact key size. So that's a good start. One a bit surprised by, oh yeah, it's beginning to become a bit better. So you in the beginning, some of you ranked RSA with 512-bit key almost at the top, and it's still pretty much tied with the others. However, this is a lot weaker than these two here. RSA with 512-bit key is something you can break in practice. I would actually say that this is even weaker than MD5 with 128-bit hashes. Again, the recommended key size for RSA is something like 3000 bits. For these two things on top, they are currently in the correct order. So what are the security levels of these? SHA-2 is a hash function, so the output size is twice as long as the security level. So this has 256-bit security, and SHA-2 is a secure scheme in general. So this should be at the top here. RSA with 128-bit keys, so RSA is generally a sound scheme, and 128-bit keys is a good key size for AES. This has 128-bit security. And the MD5 on the bottom here, so if it wouldn't say MD5 but just any hashing scheme, it would have 64-bit security. MD5 actually has a bit less than that. For RSA, I really can't give an exact equivalent here, but this is also definitely publicly breakable. So anyway, these two on the bottom here are not something you should use. These two here are totally fine. RSA is also fine with slightly larger keys, and RSA2, SHA-2, is also okay with slightly smaller hashes, such as 256 bits. Okay, then we have time for your questions if you have any. Oh no, I have another one of mine. Sorry. Namely, I already announced that next week we do have a bit more time, and in particular we do have a bit more time than I've actually planned to fill with stuff. So we do have a bit of time free if you have any special wishes about what you would like to hear. So if there's anything from the last few lectures that you would like to hear more on, or if there is a particular application you want to hear something on, or of course something related to the practicals, I can try to cover a bit of that. We don't have a lot of time, but a bit of it. Other requests here are the onion. I think this might refer to the onion layers that you have in secure browsing. I'm not sure. If this is the case, it probably overlaps a bit with privacy. I can try to do a bit of this, but many of the things that could be said about privacy actually don't have too much to do with cryptography, but are more related to higher level choices. So to choices that you make about your specific data and in your application. Okay, but still privacy seems to be quite far up, so I'll try to cook something up. Many people are requesting TLS. I was already planning to cover a bit of that, so to get to the actual protocol, so we will definitely do that. And you will also, I guarantee you, hear more about TLS than you ever wanted to hear in the network security part. So those of you who are interested in more practical stuff, be aware that what we've done so far, this crypto stuff, this was all the theory background. So in the next two parts, you're going to be a lot closer to applications. And in particular, you will learn a lot about the design choices in TLS, attacks on TLS, and other network security topics in the last part. You want to hear something about Diffie-Hellman ephemeral. This is related to TLS. Yes, we will do that next week. Handing out certificates. Yes, we will talk about certificates. Not necessarily about producing them in a specific tool or so, but explaining the ideas and their structure. Then we have requests for ECDHE and ECDSA. Doing that requires at least one entire lecture on its own, probably more than that. You will have a bit of a taste for it in the exercises. I can also come back to it a bit next week. I'm not sure in what context that would make sense, or where it would fit. Some say they want to hear more about failures, so biggest crypto fails in history and examples of cracking. Okay, so I can definitely dig out a few examples where the reason that led to a security attack was either in the cryptography or in the way the cryptography was used. We have Tor here, which probably ties in with privacy and the request for onion stuff. What else do we have here? Beans. Not sure what that should be about. Maybe it was a reply to the onions. If it's something else, please let me know. RSA practice that ties in with the protocols. What else? Tips for the test. Okay. What I think would be a good idea is if we did a longer quiz next lecture, maybe that covers the entire stuff we've done so far, to also get a bit of a feeling what the exam questions are going to be like. Is there anything else that I haven't seen yet? More cats. I can't promise that. Maybe she's busy with her flies again. We will see. Quantum attacks. Yes, this is something I want to talk a bit about. Again, talking about the details would require hours, but I can definitely cover what quantum computers in general mean for all the stuff we've heard so far. More discrete math recap. Oh no, I thought you would hate that. So if you have anything specific you would like to hear more about, maybe let me know, or if there's something you need explained again. We can do that maybe either on Discord, or if it's something specific here, then we can do it here. But the big winner seems to be hints for the practicals. We'll see what is still left open after today's exercises. So if there is still stuff that you want to know after this afternoon, it would be good to have specific questions on Discord. But what we can maybe do is try to link which parts of the exercises reflect which part of the lecture. Okay, thanks for all of these inputs. So I will see how I can take as many as possible of them into account for next week. So finally, time for your questions, although we are already running a bit over time, but I hope you don't mind. So what do we have here? You said that a good RSA key size is 3000 plus bits, but when I look at the certificate of menti.com or Google, it says 2048. Very well observed, so you actually already checked it out. If you remember, I did say that you will find many 2000 or 3000 or 4000 bit certificates. Those are the three widely used sizes that are okay-ish. The thing is that current estimates say that the security level of 2048-bit RSA is probably a bit below 128 bits. So some estimates that people make is that it's something like 112-bit security or so. But this is really hard to say because you somehow need to recompute the operations that you have in these algorithms and compare them with executions of the algorithm. And there's quite a bit of playing ground here for your estimates for how much you think algorithms will improve in the future, because unlike brute force search, in case of RSA factoring problem, we have actual algorithmic advances that mean I'm not just 10% faster because I have a faster computer, but I'm 4 times as fast or 10 times as fast because I made an actual improvement to the algorithm. So this means that it's a bit hard to compare security levels. So 2048 is okay, but it's probably a bit less than 128-bit security. So if you choose a key for yourself, you may want to do something like 3000. But you shouldn't worry too much if you use something with this size. Okay, but very good question in any case. Then what do we have? That was a better explanation of Discrete Mathematik than from Professor Lena. Thanks, that's kind of you. Actually, you may have noticed I was actually a tutor for Discrete Mathematik for a very long time, so I do have some practice on that. But thanks for your kind comment. Then what else do we have here? In one of the earlier lectures, you mentioned that constants hidden in the O notation for security claims can make a big difference. For me, no algorithms jump to mind where this constant would change more. I think what the core of this question maybe is that I say a constant like 1000 or so makes quite a difference. This is because in symmetric cryptography, at least, we try to make very concrete security claims. So saying that something has, for example, a security level of 128 bits means something very specific. It means the attack time is, for a good success probability, approximately 2 to the 128 executions of the cipher. So this is a concrete statement, not an asymptotic statement. It doesn't mean that the size just grows exponentially in the algorithm or something, or in the key size or something like that. It's a more specific statement. And in asymptotic analysis, you don't care if there is a constant of, for example, 1000 or so hidden in somewhere, but in concrete security you do, because a 1000 constant factor corresponds to a difference in the security bit level of 10 bits. And that's not nothing, that's quite a bit. So for example, if you are aiming for a security level of 64 bits, you're probably secure against casual attackers. But if there happens to be a constant of 1000 off in this estimate and your actual security is more to the 54 or so, this is suddenly a lot more practical than before. So this is because we usually try to shift or choose our parameters so that we're in the infeasible area, but not unnecessarily far in the infeasible area. And any change of the constants means we're coming closer to our boundary that we set ourselves. This is why for concrete security analysis, constants do matter. They're harder to take into account in cases like RSA, where the algorithmic analysis depends a lot more on asymptotics. Okay, the question continued. It changes more than an order of magnitude. Do you know of an example where this makes a significant difference? Okay, I see, I've been answering the wrong question. So if you're talking about orders of magnitude, I assume you mean something like tens, not just twos. So of course a factor of 10 doesn't really make a lot of impact on the attackability. If you can afford 1 core, you can probably afford 10 cores. It's not that big. But when we speak about constants in advanced algorithms, we usually speak about much, much larger constants. So for example, if you look at algorithms in the context of prime numbers for testing the primality of numbers, there you will find algorithms such as the AKS test, which is, for example, polynomial in runtime, but all the constants involved in there are huge. Meaning that even these polynomial algorithms can sometimes be slower for certain sizes than exponential algorithms. So in number theory in particular, you might run into such cases. I'm not aware of examples of big constants in symmetric cryptography, because this is not the way that analysis is usually structured. So there we usually have small constants only. Can we get the LaTeX for the stick figures? I guess so. Maybe I can post a link for them on Discord if I don't forget. It's really not exciting. It's just some vector graphics drawn in LaTeX. So if I don't forget, I will post that. And finally, I have the proof of P equals NP, but I don't have enough space to write it in here. An excellent final comment or question. So I guess that's a good end for the lecture as well. I don't see any questions on YouTube. And I see that most of you have already been leaving anyway, because we are quite a bit over time. So thanks for those who are still here, and see you again next week. Enjoy your weekend.